Hey everyone, in this video we're going to continue working with writing the area under a curve as a Riemann sum and as an integral. So here we want to, our second example, this is part 2 of our video series for that. So this is example 2, write a Riemann sum for the integral from 0 to 2, 1 plus x cubed dx using left endpoints. So that's important. So it's very specific as to which endpoints we have to use. And remember, the integral is giving us the area under the curve in the x-axis. So this area, the gray shaded area, and so I just already drew my little rectangle there. So we're going to sum all the infinitely many rectangles that we can make here. The base is delta x and the height is f of x of I star, which in this case is the left endpoint. And so the first thing is identify what's your a, what's your b, what's your function, so that then we can write it as the Riemann sum. So our definition of the integral is the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the summation I equals 1 to n, so that's our counter, of delta x times f of x sub I star. Right, the sum of the areas of each rectangle, and the area of each rectangle is the base times the height. Hence, base delta x, height is f of x of I. And so in order to go from the integral to the Riemann sum, we need to know our delta x, and we know delta x is b minus a over n, and we need our function. So in our case here, what's our a? A is the lower limit of the integral, so a is 0. B is the upper limit of the integral, so b is 2. And our function, f of x, is the thing right between the integral and the dx, so 1 plus x cubed. So our f of x is 1 plus x cubed. And so this is what we need in order to be able to write the Riemann sum. Because now with this I can say, okay, my delta x is b minus a over n, so just 2 over n. And so what's my left endpoint? So my x of I star is the left endpoint. So you can memorize the formulas for the left endpoint. You can also try to write your interval and then see how the rectangles will fall, right? So we're going from 0 to 2. So since my delta x is 2 over n, that means that our first rectangle, so this is my A1, right? My first rectangle, so the area of the first one. Since delta x is 2 over n, that means that this is 2 over n, 0 plus 2 over n. And then you go, what about a second rectangle? So if I have a second rectangle, this will be, the area will be A2, and then this is still 2 over n again, right? So it'll be 2 over n plus another 2 over n, so that's 4 over n, and so on. Then you go, what about the third rectangle? So that will be 6 over n, 2 over n plus 2 over n plus another 2 over n, and so on. So you can kind of see that then this one is my a, 0 plus delta x, and then this is my a, 0 plus 2 times delta x. And then this one is what? 0 plus 3 times delta x, and so on. So when I get to the ith rectangle, then this will be, my right endpoint will be the 0 plus I times 2 over n. And so my left one, which is the one we're after, will be, then if that's I, this is the one before it, so this will be I minus 1 times delta x. Right, so my left endpoint then is I minus 1 times 2 over n. And if you choose to remember the formulas are that the right endpoint is, what is it, a plus I times delta x. The left endpoint is a plus I minus 1 times delta x. And then the midpoint, we talked about in the previous video, is essentially the right endpoint, so a plus I delta x minus 1/2 delta x. So you can choose to memorize those, that way you know, depending on the endpoint that you're using, which one to use. If you're not specified an endpoint, just always go for the right endpoint, because that's easier than, right? Because this is the thing that you're going to be plugging into the function. So you're going to take whatever your x of I is, and you're going to plug it in for x. So notice that plugging in a plus I delta x is easier than plugging in a plus I minus 1 delta x, or this has 3 terms. So whenever possible, just go for the right endpoint. Okay, so now that we have what our left endpoint is, and the reason I'm using the left endpoint is because it does tell me to use the left endpoint. So write a Riemann sum using the left endpoint. So now I can say, okay, so I have my delta x, I already found it to be 2 over n, and I know my left endpoint is the I minus 1 times 2 over n. So, our Riemann sum, so the integral from 0 to 2 of 1 plus x cubed dx then is going to be the limit as n goes to infinity of the summation I equals 1 to n of delta x, so 2 over n, times f of xl. We're using the left endpoint. So I know this is my function. 1 plus x cubed is f of x, so let's plug it in. So I'm going to have the limit as n goes to infinity, I equals 1 to n of, I still have my delta x, so 2 over n times f of x sub l. So plug that in here, so I'm going to use brackets, so 1 plus x of l cubed. You can plug it in already, we know what the left endpoint is. I'm just trying to show all my steps for clarity, or at least I'm hoping to be clear. Sometimes I think I'm being clear and I make things more confusing. So 2 over n times, and now I'm going to say 1 plus my left endpoint cube. So the left endpoint is, we wrote it up here, I minus 1 times 2 over n. So I minus 1 times 2 over n cube. You can probably simplify this to make it better, but let's try it down here. Sometimes if I multiply this, then I guess you will have 2 terms and then cube that. So let's try it. So this is the limit as n goes to infinity, I equals 1 to n of 2 over n times bracket 1 plus, and then this thing cube. So how should we do this? Let's distribute the 2 over n. I was trying to figure out, do I cube, do I do I minus 1 quantity cube and then 2 over n cube, or, but either way you have to multiply the 2 over n through anyway, so let's just multiply it in as we go. So this will be 2I over n, and then minus 2 over n, and then that's cube. Right, the thing that I'm cubing, so who does the cube belong to? It just belongs to this quantity in the inner bracket, not the 1. So I'm not cubing the whole thing, I'm just cubing this. So I'm distributing that 2 over n I into it. Can you see why we rather use the right endpoint? And then cube that up. So I'm going to have the limit as n goes to infinity, and all this lovely stuff that we have to write. And now let's see, 1 plus, and now cube that. And you may want to use the a plus b cube formula, right? That tells me that that's a cube plus, what is it? You can use Pascal's triangle to remember how it goes. I think it's, what does it go? A squared b plus b squared a, and then plus b cube. So, so let's see, so what does that become? So that will be 2I over n cube. So that will be 8I cube over n cube, and then plus a squared b. So actually minus, right? Because b is the minus 2 over n. So minus a squared b. So 2 square, I square, n square, and then times b. So once you multiply everything out, this is what you should get. So I encourage you to try that on your own and make sure that we get the same thing. So then this will be limit as n goes to infinity of I equals 1. And what are we doing? What's the goal? So this is 2 over n, and then I guess here there's not much to do other than get rid of those parentheses, but there are no like terms. The thing I could do then is distribute this 2 over n in to everything. There are different ways to approach this. I could also think of factoring out the 2 over n out of the sum, right? Because the I is the thing that's changing in the sum. So I could factor the 2 over n, treat it as a constant outside of the sum. But I'm going to multiply it in. So I'm going to have 2 over n times 1. So plus then 16 I cube over n times n cube. So n to the 4th minus 16 I square over n to the 4th plus 16I over n to the 4th, then minus 16 over n to the 4th. And so this is now my sum. Now our goal is to be able to use those formulas. So when I ask why are we doing this, how do you know when to stop? You know when to stop when you can use the formulas, which were way at the beginning here. These useful formulas. So let me copy them and bring them down with us. So now that I have the formulas down here, I can try to see, okay, where can I use them? And so I see, I'm going to try to group together the constant terms. I have 2 over n and negative 16 over n to the 4th. Don't worry about getting a common denominator. And then we have the other ones. So this has an I cube, and so I'm going to be able to use that one. And then this one has an I square, so I'm going to be able to use that one. And so you kind of see what we're doing. So the goal is to simplify the Riemann sum enough so that we can pick out and see how we're going to use these formulas. So let me split up the sums. So this is going to be limit as n goes to infinity of the constant term. So this is going to be sigma I equals 1 to n of my constant term is 2 over n minus 16 over n to the 4th. And I don't need to get a common denominator there. Plus, and then the sum of I equals 1 to n of, so I'm going to write it as 16 over n to the 4th times I cube. Right, that's a constant, so I can use the sum of the I cube. So I can then replace sigma I cube with this formula. And then plus sigma and the I square. Oh, that's a minus. Minus sigma, and it's 16 over n to the 4th again, I square, and then plus sigma 16 over n to the 4th, that seems to be the common term, I. And now I can use my formulas. So this, I still have my limit as n goes to infinity of the first one. This is just a constant. There's no I in here. So this is like a C, right? Remember again, n is a fixed number. So if I was using 16 rectangles or 8 rectangles, this will be I equals 1 to 8. And this will be 2 over 8 and 16 over 8 to the 4th. So this is just a constant because there's no I in this formula. So I can use the first one. So it will be n times c. So this is n times 2 over n minus 16 over n to the 4th. And then plus, now here, the 16 over n to the 4th, that's a constant that I could pull out to the outside, and I really just have then the summation of I equals 1 to n of I cube. So it's this guy. So let me distribute the square as we go. So this will be times n square, n plus 1 square over 4, right? Distributing this power in. And then minus, same thing here, I can pull out the 16 over n to the 4th out of the sum, and I have the summation of I square. The summation of I square is n times n plus 1 to n plus 1 over 6. So n times n plus 1 to n plus 1 over 6. And then my last one is the summation of I. So plus 16 over n to the fourth. I can pull that again out of the summation and have the summation of just I, which is n times n plus 1 over 2. Now as we take the limit, let's see, can we simplify anything? So I'm going to have my limit as n goes to infinity, bring this n in. So when I multiply the n times 2 over n, I just get 2 plus 16 over n cubed, right? N times 16 over n to the fourth, one of the n's cancels. And what about here? So 16, I can reduce it with the 4, I suppose. So that gives me 4. N squared and n to the fourth, that becomes an n squared. I'm just trying to think, how can I simplify this? So 4 n plus 1 squared over n squared. On the bottom, minus, this is getting a little harder to do, right? So I'm going to have 16. I'm going to just put the constants together. Then 16 over 6, and I'm going to have n times n plus 1 times 2n plus 1 over n to the fourth. I'm not going to try too hard to simplify that anymore. 16 and 2, that reduces to 8. So plus 8 n times n plus 1 over n to the fourth. And one of the reasons I'm not trying too hard to simplify is that I'm noticing the powers as I go. The power in the numerators seem to be getting smaller than the power in the denominator. Right? Notice the last one. When I multiplied n times n plus 1, then my highest power there is going to be n squared. But the power on the bottom is n to the fourth. So as n goes to infinity, right, n is going to infinity, then that means that that last one is going to go to 0 because the power on the bottom is larger. Same thing here, n times 2n, that's going to give me a 2n cube. But I have an n to the fourth on the bottom, so the power in the denominator is larger, so that's going to go to 0. What about here? Highest power in the numerator will be n squared. Highest power in the denominator is also n squared. So what is this limit going to be? That's going to be the ratio of the coefficients, so just 4. And then here, as n goes to infinity, 16 over n cubed goes to 0. So my limit, right, as I'm taking the limit, I don't write limit anymore. So this is just going to be equals 2 plus that 0 plus this one. Powers are the same. So as n goes to infinity, that's just going to be 4. And then all the other ones are 0. So I get 6. So that should be the area under the curve y equals 1 plus x cubed. Oh, I did not draw this correctly. That should have been up 1 plus x cubed from 0 to 2. So this should be shifted up 1. I drew y equals x cubed instead of 1 plus x cubed. And so, but the area is going to be 6. So after all of that work, the number turned out to be nice. So this is probably one of the hardest ones just because you have the cubing portion. We have to deal with this cubic and you have to use the a plus b, or there's another one for a minus b. That probably should have been the best one to use, the a minus b cube. You can find them in your book. They're very similar, but so you use those formulas and then multiply it out, gather your like terms, and remember the goal of this Riemann sums is to try to get to this. Now some of you may have already taken calculus at some point and know how to do an integral. You may be asking like, why are you doing this when you can just do the evaluate the integral like that? But on a quiz or a test, if I'm asking you to evaluate using a Riemann sum and you just do an integral by using the shortcut methods on the future sections after the fundamental theorem of calculus, unfortunately that's not going to get you any points because what I'll be testing is, can you evaluate a Riemann sum? So know how to do this, I guess is what I'm trying to say. All right, last example is, given a Riemann sum, can you write the integral? So something like this. Given the Riemann sum, express the limit as a definite integral. So going backwards. So in this prior example, we were given the integral, which represents the area under a curve, and ask you to write it as a Riemann sum and evaluate it. Once you evaluate that Riemann sum, you get the exact area. So now we're trying to go backwards. Given the Riemann sum, can you write the integral? So the key with this is to think about what the definition of the integral is. We know the integral from a to b of f of x dx is equal to the limit as n goes to infinity of the summation I equals 1 to n of delta x times f of x sub I star. And so really what we've got to do is compare what's inside the sum. So here's my sum. I have the limit, summation I equals 1 to n, summation I equals 1 to n. So I'm really comparing what's inside here. So I know, okay, so this 2 over n appears to be my delta x. So I can say then delta x is 2 over n. I also know that delta x is b minus a over n, right? So from here, I know I can conclude that b minus a is equal to 2. So the distance, the length of the interval is 2. So now, what's my f of x of I star? So remember, x of I star can be the right endpoint, the left endpoint, or the midpoint. And so this is where maybe memorizing the formulas is nice, because I know the right endpoint is a plus I delta x. The left endpoint is a plus I minus 1 delta x. So I'm looking for these things in here. So I see that I have an I, not an I minus 1. So I must have the right endpoint or the midpoint, but I don't see a half for the midpoint. Remember, the midpoint is a plus I delta x minus 1/2 delta x. So I don't see that extra part. So this must be the right endpoint. So x of I star then is the 3 plus 2i over n, right? So this is 3 plus I delta x. And so this matches up because I know my delta x is 2 over n. So that matches with this. So that means that a must be 3. So far I can say, okay, so is 3 2 something of then my function dx. So can we figure out what that top limit is? Yeah, we already said the length, because delta x is 2 over n and delta x is b minus a over n, that the b minus a is 2. The length of the interval is 2. So if my lower limit is 3, right, then I gotta go, so it's going to be 3, 2, add 2, that's going to put me at 5. So then I know then my integral should be the integral from 3 to 5 of, and now my function dx. So what's f of x? And so we compare this, right? This delta x times f of x of I star. This is my delta x, so this should be my f of x of I star. So this is our right endpoint, and it's being cubed. So that means that the function must be x cubed. So I can say this is the integral from 3 to 5 of x cubed dx. There are other ways that you could approach the problem, right? You could have said this is the integral from 0 to 2, because you see that your delta x is 2 over n. So you could say, right, it could be the interval from 0 to 2, because then that length is still 2. Your delta x will still be 2 over n. But then how would that change your integral? Now you have to go from 0 to 2, and so my function, instead of being x cubed, is going to be, right, this is going to be then 3 plus x of I star and then cube. So my function will be 3 plus x and then quantity cube dx, so that then your x sub I star can be just replaced by 2I over n, still the right endpoint. So there are different ways, right, that you can approach it. There you can have multiple answers for this. It just really affects then how are you choosing your interval based on your delta x. So it kind of goes based on the delta x, but it can also be based on the function. Like here I chose to see my x of I star as the whole thing, 3 plus 2I over n, which then that led me to think that A is 3. But you could have let your x of I star just be 0 plus 2I over n, and then the 3 now becomes part of the function instead of part of the endpoint that I'm using. Hopefully that makes sense. But yeah, so when you see a Riemann sum and you have to write the integral, compare the definition. So you're looking for a delta x and you're looking for your function. And then, right, your x of I star that is embedded in there in the function is either going to be your right endpoint, your left endpoint, or your midpoint. So you got to be looking at, do I have an I? Do I have an I minus 1? Or do I have this funky midpoint one? And then go from there. So I like those because they're kind of fun. They're like little puzzles that you have to figure out and put together. All right, email me if you have any questions.